So welcome everybody to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, I'd like to thank very much Professor Michael Shulman, who kindly accepted our invitation. Michael, thank you very much. Even in this so busy day, you are here to give this talk.
Thanks for the invitation. Yeah, so the references to the fact that I just gave a seminar at the Lógicos Institute earlier. It's a funny world now in which I can talk in California and Brazil on the same day. Right. So so this talk is called Affine Logic for Constructive Mathematics. I don't know whether I have the right sense for the sort of background that people have, so please feel free to stop me if I say anything that doesn't make sense and ask me to explain it. I will be very happy to try to make sure everybody is on board. First I want to say a little bit about constructive mathematics, and then I want to say a little bit about this thing called affine logic, and then I want to relate them together with something that I'm calling the antithesis translation. I'll explain what that is. Okay, so constructive mathematics historically arose in around the late 19th and early 20th centuries as sort of an opposition to an increasing trends of abstraction in like Cantorian set theory and so on. And a various group of people like Kronecker, Poincaré, I'm missing a letter here, Weil, and especially Brouwer and Heiting, names are associated with this development. And they reacted to this by insisting that a lot of these new non-constructive proofs really shouldn't be allowed, that they really only wanted to let proofs that are constructive. So what do we mean by constructive? A lot of mathematicians have some informal sense for what it means for a proof to be constructive, but here's an example of a non-constructive proof, just to have something to look at. So this is a classic proof that there are irrational numbers alpha and beta, such that alpha to the beta is a rational number. So how do we prove that? Well, suppose for contradiction the opposite, that alpha to the beta was always irrational when alpha and beta are rational. And then consider the case when alpha and beta are both the square root of 2. That would tell us that the square root of 2 is irrational. But now, since we know that square root of 2 to the square root of 2 is irrational, we can take that to be our alpha, and then take beta to be the square root of 2. And then when we raise that to the power root 2 to the root 2, if we raise that to the further power of root 2, then the root 2's become a 2, and that squares to 2, which is a rational number, and that's a contradiction, because our assumption would tell us that it's irrational. So that proves the theorem, but it doesn't tell us anything about what the alpha and beta are, that are irrational numbers whose power is alpha to the beta is rational. And that's kind of disconcerting or unsatisfying. If we're saying that something exists, we would like to be able to find it. It is a proof to a classical mathematician, but Brouwer and Heiting and these folks didn't want to consider it a proof. They only wanted to do proofs that were constructive. So the way they did it was they came up with a different kind of logic, basically, which is nowadays often generally called intuitionistic logic, although there are historical issues with using that word. But now that's the way it is. And it has the property that any valid proof in this different logic is always constructive. And the way it does this is basically it forbids proof by contradiction in general. So for something can be not false without necessarily being true. If you assume that it's false and you reach a contradiction, then it can't be false, but that doesn't immediately tell you that it's true in the constructive sense. Related to that are other properties like De Morgan's laws. Most of them hold, but not the one that tells you that you can conclude that one of two things is true, because it might not give you a way to conclude which of them is true. And so you haven't constructed a proof of one or the other. The negation of a for all statement doesn't give you an exists because you haven't constructed such a thing. And the law of excluded middle doesn't hold because it doesn't give you a way to tell you which of them is true. It doesn't give you a way to decide or construct a proof of either P or of its negation just by knowing that they're opposites. What is this precisely? We can define it in a concise way from an algebraic perspective by saying that classical logic uses Boolean. To be more precise, we can describe intuitionistic logic algebraically by saying that just as classical logic uses Boolean algebras, intuitionistic logic uses Heiting algebras, which are a sort of weaker structure. So a Boolean algebra is a lattice that has complements, whereas a Heyting algebra is a lattice which has implications in this sense. So there's an operation which takes any two elements to an element, which Q implies R, that I'm writing like this, which is characterized by this property, that P is less than or equal to Q implies R precisely when P meet Q is less than or equal to R. And you can, this is sort of like the deduction theorem, I guess you could call it in logic, that the way to prove an implication is to assume the hypothesis and then prove the conclusion. And when we have a Heyting algebra like this, then we can define negation in terms of the implication as if P then false. P implies a contradiction, where that false is the bottom element. And that this gives us all the characteristic properties of intuitionistic logic, right? So this negation is not involutive, not P is not the same as P. De Morgan's laws hold except for this one. We don't have excluded middle and so on. You can generalize it to predicate logic in fairly straightforward ways. So, for example, of course, any Boolean algebra is a Heyting algebra where you define implication in terms of complements and disjunction in the usual way. But there are other interesting examples. For instance, the open set lattice of a topological space is a Heyting algebra where the implication U implies V is defined as the union of all open sets whose intersection with U is contained in V. So you basically sort of take this universal, this property of implication that defines it, and use that as a definition with the union property. So there's all sorts of different directions you can go from this, right? This leads into like topos semantics and topological sheaf semantics for intuitionistic logic and so on, which is one of the reasons that a lot of people nowadays are interested in it, not because they have some philosophical attachment to all proofs being constructive, but because it's more general and it applies to Heyting algebras and sort of logic built on topological spaces and so on. But that's not the direction I want to go today. Instead, I want to call attention to one particular aspect of intuitionistic mathematics, which arises in particular when we try to do analysis. So suppose we define a real number the way we do classically, one of the ways we do classically as an equivalence class of Cauchy sequences, and then equality of Cauchy sequences, maybe we take some kind of a quotient. Equality of Cauchy sequences means that they get as close as you want. So for any epsilon, they can become epsilon close. There's a natural number n such that as long as we're that far out in the sequence, x and y, our Cauchy sequences, are that epsilon close to each other. Now, we'd expect the real numbers to be a field, but in constructive mathematics, saying that something is non-zero is not enough to define an inverse to it, because just saying that it's non-zero in the sense of not equal to zero in this way, right? So that means that it's not the case that for all epsilon greater than zero, there's a something or other. But for all and not don't commute with quantifiers the way they do in classical logic. So that doesn't let us conclude that there exists some fixed epsilon that bounds it away from zero, so that we can find infinitely many terms of x that are that far away and then invert them to make an inverse Cauchy sequence. Right, so x might be not zero in this sense constructively without being able to find an inverse to it. So the solution to that is to introduce a stronger notion of inequality. So constructive mathematicians define two numbers, real numbers, to be apart from each other, which was written with this sort of stronger notion of slashed equals, if they do satisfy this notion, that there exists an epsilon which bounds them apart from each other, so that once you get past some point, the values of the Cauchy sequence are always epsilon apart from each other. And then you can prove, even in intuitionistic logic, that if x is apart from zero, it does have a multiplicative inverse. So Eric Bishop was one of the founders of modern constructive analysis, and he wrote in general that it is not necessary to define inequality in terms of negation, but it's better to introduce an affirmative notion of inequality, such as this kind of apartness. So this sort of thing is common when trying to do mathematics constructively in intuitionistic logic. Things that are normally classically defined in terms of negation don't work very well. You generally want to introduce some different sort of thing which behaves similarly classically, but constructively is better behaved because it's more affirmative. All right, so that's my quick introduction to constructive mathematics. So now here's my quick introduction to affine mathematics or linear mathematics, which is a little bit more general. So there's an old joke where the patient goes to a doctor and says, "Doctor, it hurts when I raise my arm," whatever. And the doctor says, "Well, don't raise your arm." So analogous to that, you might respond to the constructivist who says, well, we define negation to be P implies false, but then this definition of negation isn't really useful for anything. Well, don't define negation like that. If you want to define negation in a better way. So how else could we define negation? Well, we could define negation as the formal De Morgan dual. If we want to define the negation of an or, well, it should be an and. If we want to define the negation of an and, it should be an or. The negation of an exists should be a for all, and the negation of a for all should be an exists. And this, I think, can be justified even from a philosophically constructive point of view by saying, well, when you prove an existence statement constructively, what does that mean? You should provide an example. That's what it means to construct something. But by the same token, when you disprove a for all statement constructively, well, you should provide a counterexample. That's what it should mean, really. I would argue, to constructively disprove a for all statement, you should provide a counterexample. And that's what this means. And that will make the De Morgan laws hold, all of the De Morgan laws hold, and similarly for the quantifiers. But in what sense is it constructive? I mean, yes, it seems like if we do this, then maybe it's going to make things non-constructive because it does satisfy this proof by contradiction, right? This formal De Morgan duals, right? We just push the negation through, and we push a double negation through, and then sort of it trivializes the double negation back to the original formula. So it seems like proof by contradiction would be allowed, but that makes it seem like things are not going to be constructive anymore. So that leads us to think back about what's not actually non-constructive about proof by contradiction. And it's not what we think. So suppose we're trying to prove an existence statement by contradiction. Well, we assume it's negation, which, according to our definition of negation now, is that that every x does not satisfy P. Now, how do we use this hypothesis? How do we use the assumption that every x does not satisfy P? Well, we have to give a particular x and use instantiation, universal instantiation, to conclude that that particular x does not satisfy P. So it seems like we've given an example. We have constructed something in order to give a proof by contradiction. So the problem comes if we do that more than once. We don't know which example that we've provided is the counterexample. So here's our non-constructive proof again. We suppose for contradiction, the negation, right? This is exists. We're trying to prove it by contradiction. We suppose the opposite, that for all a and alpha and beta that are irrational, alpha to the beta is also irrational. And then we instantiate this twice. First, when alpha and beta are both the root of 2, and second, when alpha is root 2 to the root 2 and beta is root 2. And then we get a contradiction, but we don't know which of these two examples, which of these two instantiations gave us the counterexample. So the non-constructivity from this point of view comes not from the proof by contradiction, but from using the contradiction hypothesis more than once. So what we can do instead of forbidding proof by contradiction, we can use what's called a linear logic or an affine logic, which prevents us from using a hypothesis more than once, at least in some cases. This is so the algebraic version of this is sometimes called a Girard algebra in honor of Girard, who invented and studied linear logic. So this is a lattice again, but now in addition, it has a commutative monoid structure on it, which is different from the meet and the join of the lattice operation. I'm writing it as this monoid operation as tensor. So it's an operation that preserves the ordering, the partial order. And this tensor is sort of like a conjunction. You should think of it as kind of like a version of and, but it doesn't satisfy duplication, doesn't satisfy contraction. So x might not be less than or equal to x tensor x. In contrast to the way the join, the meet in a lattice is idempotent. Now, once we have this different kind of conjunction, we can give ourselves a negation, which is actually an involution. So the double negation is back to the original thing we started from. It reverses the order on the lattice, and then it satisfies this funny property, which is kind of like the hiding algebra property. And I'll come back to that later on. But for now, basically, it says that this thing here is acting kind of like an implication. Similarly to the way it did in the hiding algebra case where we had the meat over here. I'm going to be Girard algebra is the algebraic version of linear logic. I'm going to be mostly interested in the version of affine logic, which allows us to not use a hypothesis if we want to, even though we're not allowed to use it more than once. And in that case, the Girard algebra is semi-Cartesian. So that means the top element of the lattice is also the unit for the monoidal structure. So x tensor top is equal to x. So it's a semi-Cartesian Girard algebra, which represents what's called affine logic. And again, you can deal with quantifiers in sort of a more or less standard way. So here's a sort of an algebraic version of proof by contradiction in a Girard algebra. So to prove that that assuming P we get Q, that's the same as proving that assuming P we get the double negation of Q. And now I can throw in, because the top element is the monoidal unit, I can throw in a tensor with the top element. And the top element is the same as the negation of the bottom element. And now this is a thing of the form to which I can apply this if and only if. I move my not Q to the other side. So in other words, to prove Q, assuming some hypothesis P, it's the same as to assume the negation of P in addition to my hypothesis Q and derive a contradiction from it. But we don't have this duplication. So I can't take my not Q, for instance, in particular. I can't take my not Q and derive two copies of not Q from it. So I can't use my contradiction hypothesis more than once. And that sort of keeps it constructive in an intuitive sense. In practice, sometimes we do want to use things more than once, and so Girard introduced these exponential modalities, bang, which you can put in front of something, and that allows it to be used more than once, but then you can't do perfect contradiction on it anymore. So it's kind of more complicated than that, but that's sort of not something I want to get into today. So this is the basic idea of affine logic. So I mentioned before that the monoidal product here is kind of like an and. It's a conjunction. And it allows us to use both of the conjuncts only at most once. We also still have the lattice meet, which is a different kind of conjunction, which Girard called additive, as opposed to the multiplicative monoidal one. And the additive conjunction, informally, it only allows us to use one of the conjuncts, but we get to choose which one to use. But it does satisfy this diagonal property. In fact, it's idempotent. There's actually inequality, just like any lattice operation. We also have the lattice join, which is a disjunction, which is kind of like the meet. But there's also a multiplicative disjunction that we can define by basically applying De Morgan's law to the multiplicative conjunction. We negate things, we apply the tensor, and then we negate the result again, and that acts kind of like an or. Girard used this funny upside down ampersand symbol for it, and that's sort of the standard one now, although a lot of people use a lot of different symbols for it. It's so these things satisfy all the De Morgan's laws, but they sort of stay in the same world, right? So the additive things satisfy De Morgan's laws in the additive world. The multiplicative things satisfy De Morgan's laws in the multiplicative world. The quantifiers, which are kind of like infinitary additives, satisfy their De Morgan's laws, relating them to each other. And there's also an implication, an if-then, which is denoted with this lollipop symbol. And it's sort of, again, it's linear or affine in that it only allows us to use the hypothesis once. And you can define it in terms of the multiplicative or in the same way that the classical implication can be defined in terms of the classical or. And this then satisfies contraposition, and it also tells us a little bit more about how to think about this multiplicative disjunction, because it's equivalent to if not P then Q, or also to if not Q then P. So sometimes people pronounce this as par, but I think a more suggestive way to pronounce it is P or else Q, or P unless Q. This last one says, unless Q is true, then P must be true. In other words, if Q is false, then P must be true. So the excluded middle fails for the additive disjunction, but the excluded middle is true for the multiplicative one. And I like to think about it as saying the additive disjunction supports the proof by cases, but the multiplicative disjunction supports the disjunctive syllogism. So two different ways of reasoning about a disjunction. In linear or affine logic, we separate them into two different connectives. And so here's how this solves the problem of apartness or inequality for real numbers. If I define, here's my definition of equality for real numbers using Cauchy sequences. In linear or affine logic, now we have this complete De Morgan duality. And so if I just negate this equals with a single slash, that's just a not sign in front of it. But now I can push that through, right? Not for all becomes exists not. Not exists becomes for all not, and so on. And that gives me precisely the intuitionistic definition of apartness is the affine or linear definition of inequality. I don't need to introduce something new. It's already there as the negation of equality. And then you can prove in affine logic that the real numbers are actually a field in the more intuitive sense that anything not equal to 0 has a multiplicative inverse. So the affine logic, at least intuitively, it's better behaved than intuitionistic logic in at least this way. But it's maybe a little hard to understand, right? So especially, I mean, intuitionistic logic is hard to understand too, maybe. But we can understand them both better if we could have some sort of a translation into a logic which we understand better, one way or another way at least. So there's a classical example of such a translation is the double negation translation of classical into intuitionistic logic. And I can express that algebraically by saying that if I have a Heyting algebra, then I can construct a Boolean algebra from it by looking at the elements that are fixed by double negation. So for instance, if I start from the open set lattice of a topological space, then this gives me what are called the regular open sets, the ones which are the interior of their closure, I think, is the way of saying it topologically. And so you can use this is an algebraic description of it, but you can also use it to translate a proof in classical mathematics into a proof in intuitionistic logic, where you sort of change the statements that you're proving by adding double negations on things. Right? So in other words, classical mathematics can still be done by a constructive mathematician. It's just that they're proving something which is sort of weaker than they might want because it has double negations in front of things. Now, this algebraic version of thinking about the translation can be characterized universally in the way that algebraic constructions often are. So it has a universal property in the following sense. It's adjoint to the forgetful functor from Boolean algebras to Heyting algebras. So what does that mean? Anybody who may not be familiar with that language, if I have a Boolean algebra, it is also a Heyting algebra, as I said before. And if I have a Heyting algebra and a Boolean algebra, then I can talk about Heyting algebra homomorphisms from a Heyting algebra H to my Boolean algebra B regarded as a Heyting algebra. So a Heyting algebra homomorphism is a map which preserves all the Heyting algebra structure. So it's a lattice map. It preserves the ordering and the meets and the joins and the top element and bottom element, and also the Heyting implication. And the universal property says that every Heyting algebra homomorphism from H to B to a Boolean algebra is bijectively related to a Boolean algebra homomorphism from this double negation thing into B. So there's a natural bijection between Heyting algebra maps like this and Boolean algebra maps like this. And the word natural is a formal thing in category theory that means that this bijection respects composition on either side with morphisms between H's and between B's. So having this kind of bijection, natural bijection like this, is what it means to say that this double negation construction is left adjoint to the forgetful functor from Boolean algebras to Heyting algebras. And it's left because this operation appears on the left of our homomorphisms. There's also a right adjoint, which takes a hiding algebra to the subset of complemented elements, such that their union together with their negation is the whole thing. So these are the elements that satisfy excluded middle. The other ones are the ones that satisfy double negation. So this algebraic way of thinking about this translation has a bunch of advantages. So it characterizes something uniquely up to isomorphism. So even if I didn't know how to define this H double negation, asking that there is such a thing with this property would characterize it. Anything else that has this property is isomorphic to it. I can study it abstractly as well as having a concrete construction of it in terms of the double negation fixed things. And finally, even if I didn't already have the translation, I could invent the translation by saying, well, here's a universal property that it might have. Let's see if I can construct such a thing. Okay. So that leads us to a way that we might try to translate linear logic into intuitionistic logic or classical logic by looking for some sort of universal construction relating Girard algebras to hiding algebras or Boolean algebras. So we need some kind of a forgetful functor to ask for an adjoint of some kind. Now, it's not the case, as it was in the intuitionist case, it's not the case that every Girard algebra is a hiding algebra or a Boolean algebra, but there's an intermediate thing which they are both of. And it's called a residuated lattice. So a residuated lattice has some of the structure of a Girard algebra and some of the structure of a hiding algebra. It sort of puts them together as sort of like an intersection of the two. So it's a lattice. It's also a commutative monoid. So like a Girard algebra, it has a tensor. It has this multiplicative conjunction, which is not the same as the lattice meet. And I'm thinking about only the semi-Cartesian affine case, so the monoidal unit is the top element. But now instead of the negation, instead of the involutive involution like that a Girard algebra has, instead it has just an implication that acts like the linear implication in linear logic, and also like the implication in a hiding algebra, but relating to this multiplicative, this monoidal tensor rather than the lattice meet. So in other words, to prove Q implies R from P, it's equivalent to assume Q in addition to P and prove R, where this in addition to is this multiplicative conjunction. So these semi-Cartesian residuated lattices include hiding algebras on the one hand, in the case when the monoidal structure is actually the meet in the lattice. That gives exactly a hiding algebra, right? Then this reduces to the hiding algebra property. And they also include the semi-Cartesian Girard algebras. Those are the residuated lattices where the double negation in this sense is involutive, right? So just like in a hiding algebra, we can define negation as implication into false. In a residuated lattice, we can define implication as, we can define negation as implication into false. Just as in a hiding algebra, that's not necessarily involutive, but if it is, that we have exactly a Girard algebra. And then this property reduces to the Girard case. So the defining if and only if thing for a Girard algebra can be seen as essentially saying that if you define implication as in terms of the monoidal structure, then it is a residuated lattice. It does satisfy this property. So now we have this notion of residuated lattice, which includes the hiding algebras at least, and we have a forgetful functor from Girard algebras to residuated lattices. And now I'm going to describe an adjoint to this functor. So just like the double negation thing, H double negation is a way of making a Boolean algebra out of a hiding algebra. Now this is going to be a way of making a Girard algebra out of a residuated lattice. So this is called the Chu construction. It's actually, the Chu construction is actually much more general than this. It applies to not just lattices and posets, but also categories and even multi and poly categories. But in this particular case, this is what it does. So if L is a residuated lattice, Chu of L is going to be a Girard algebra. So it's, in particular, it's a lattice. Its elements are pairs of elements of L, which are incompatible in the monoidal sense. So if I tensor them together, I get the bottom element. So you should think about this as saying that a truth value in Chu-Evel comes with a way to assert it and also a way to refute it in such a way that I cannot both assert something and refute it. Right? If I assert it and refute it, then that's contradictory. So P plus is the assertion and P minus is the refutation. And then all of these other definitions, well, most of the others follow from that. So, right, when does one of these things less than or equal to another one? Well, if I assert P, then I should also be able to assert Q. But conversely, contrapositively, if I refute Q, I should also be able to refute P. So that's the notion of entailment in this poset. The lattice operations are all pointwise. What does it mean to assert P and Q? Well, I assert P and I assert Q. What does it mean to refute P and Q? Well, I could refute P, but I could also refute Q. Either of those would count as a refutation of P and Q. The tensor product has the same, sort of behaves the same on the assertions, at least, although it's the multiplicative tensor, but the definition on the refutations is different. It says if I assert P, then that counts as refuting Q, and if I assert Q, that counts as refuting P. So that's a different way of saying that P and Q can't both be true. And the negation just flips the assertions and the refutations. So here I've sort of got, I sort of ended up saying that in words on the last slide, but here's a description of it. And when I say the antithesis interpretation, what I mean is this interpretation or translation of affine logic into intuitionistic logic that acts like this Chu construction on algebraic representations. So we have a hiding algebra in propositional intuitionistic logic. We regard it as a residuated lattice, and then we make it into a Girard algebra through this Chu construction. So in other words, if I have a statement, a theorem in affine logic, then I can translate that into a theorem in intuitionistic logic, where all of my statements sort of end up having two pieces. There's an assertion part and a refutation part. And all of these operations in affine logic translate into operations on the assertions and the refutations in intuitionistic logic. So to end, I want to throw a whole bunch of examples at you. And I'm not expecting you to understand all of these examples, but I want to convey the general picture that really shocked me when I first wrote this down, when it first occurred to me that you could do this, looking at the Chu construction and so on, which is that there are a lot of things that constructive mathematicians do in order to make things work constructively, which look really weird, but they arise automatically from this antithesis translation, from something that's written naturally in affine logic. And I find this really inspiring because linear logic, which is sort of the parent of affine logic, was originally conceived as a constructive logic with an involutive negation. So he wanted to have something that's constructive in an intuitive sense of constructing things when you prove them. But for some reason, in the 40 years since he invented it, nobody has started using it, maybe 30 or 40 years. Nobody has started really using it for doing constructive mathematics. And there are a lot of reasons that might be the case, but I think having this translation may actually help connect these two worlds a little bit more. The first example is a more general kind of apartness. So I defined apartness for real numbers in a particular way. More generally, constructive mathematicians often talk about sets that are equipped with an abstract apartness, which satisfies a bunch of axioms like it's symmetric, it's irreflexive, and it satisfies some sort of counterpart of transitivity. And all of these come automatically from writing the ordinary equivalence relation properties of equality in affine logic and translating them across the antithesis interpretation. So for instance, if I have this linear implication, remember an implication in this true construction consists of saying that you go one direction on the assertions and the other direction on the refutations. So this single relation in affine logic consists of both an assertion and a refutation, which in the refutation behaves like this apartness relation. And this symmetry property implies that both of these are symmetric, because you go in one direction in one, in the other direction in the other one. And the transitivity for this relation in affine logic translates into two different implications, one for equality being transitive and one for the apartness being sort of co-transitive, you might say. And then there are a bunch of others. So order relations often come with both a strict version and a non-strict version, which are related in some way, and that comes from a single order relation in affine logic. Subsets often come with sort of a specified complement, which may not be literally the negation complement that comes from having a single subset in affine logic. Functions are often required to be strongly extensional. In other words, they reflect apartness. That comes automatically from saying they preserve equality in affine logic. Sets are often required to be inhabited, which is sort of a stronger statement in intuitionistic logic than saying they're not empty. But in affine logic, saying they're not empty implies that it's already inhabited by passing to the dual, the refutation. Groups are often, and other algebraic structures often come with apartness, and instead of considering a subgroup, we also often consider an anti-subgroup, which is like the formal complement of a subgroup that comes automatically from having a subgroup in affine logic. Ideals come with anti-ideals and so on. Topological spaces come with both, often come with an apartness relation between points and opens and sets. And those relations for that also come automatically from formulating a topological space in affine logic and so on. So all of these definitions in the right-hand column, which I blew through really, really fast, are just defined by constructive mathematicians just for practical reasons, because they wanted to be able to do the mathematics. But they look weird and they backward to a classical mathematician, and working with them formally requires a lot of sort of backwards bookkeeping that's easy to get wrong. But when we write things naturally in affine logic and pass across this translation, it automatically keeps track of all of these anti-subgroups and apartnesses and complements and so on when we translate it into intuitionistic logic. So that's the takeaway. That's one of the takeaways, that this antithesis interpretation is neat. And the other one that I kind of wanted to emphasize too is that these universal properties of a translation can be useful for figuring out how to relate different logics to each other. And that's all I had to say.
Thank you very much, Mike. So, as usual, now we have time for questions or comments. Juan?
Hi. So, great talk. Thanks. I've taken a look at that paper, but I have some doubts. Not really doubts. The point is, I consider myself a constructive mathematician, and I work with constructive systems. I like to develop my research in intuitionistic type theory, and there is quite a difference between understanding the formal properties of a logic and knowing how to work within that logic. So in intuitionistic logic, we have, for example, the BHK interpretation, which says that, well, to prove an implication, you have to provide a procedure that transforms proofs of the assumption into proofs of the conclusion. To prove A and B, you have etc. Do you know of any interpretation of affine logic that would provide an intuitive understanding of how to work with linear logic, making it practical?
Well, I regard this as such an interpretation. So the BHK interpretation says to prove P implies Q, you give a procedure transforming proofs of P into proofs of Q. The antithesis interpretation says to prove P implies Q, you give both a procedure transforming proofs of P into proofs of Q and a procedure transforming refutations of Q into refutations of P.
Okay, makes sense. So the follow-up question is, have you tried to do any actual mathematics with affine logic?
Yes, not a huge amount, but a certain amount. So you can the paper that the way I wrote it doesn't actually work natively in affine logic very much. It's mainly focused on the semantic translation, saying I write these definitions in affine logic and I translate them into constructive logic and I see what I get. But you can also take those definitions and prove things about them in affine logic. And using this sort of interpretation as a guide, and you get up with theorems that are that act like the sort of the translations of the theorems that you expect to have in intuitionistic logic.
Okay, thanks.
So I think I haven't done a whole lot of it, but I've done a little bit. I did prove basic properties of real numbers and some things about maybe metric spaces or algebra groups or rings. I think it's I wouldn't hold this up as an interpretation of affine or linear logic that's definitive for that logic in the same way that BHK could be argued to be definitive for intuitionistic logic, because among other reasons, this interpretation validates a bunch of things which are not true in general in affine or linear logic. For instance, in the antithesis interpretation, the additive conjunction distributes over the additive disjunction, which is not true in general in affine or linear logic. So I think this interpretation could be helpful in learning to work with affine or linear logic. But if one really wants to work natively in affine or linear logic without always thinking of it in terms of intuitionistic logic, one eventually is going to have to go a little bit further and get a little bit beyond this antithesis interpretation. Well, but this can still be useful, even if all we care about really is, say, intuitionistic type theory. This interpretation could still be useful to keep track of all the apartnesses automatically, and then actually do the translation when you want to do something that's not inside the linear fragment.
José?
Thank you, Bruno. Thank you, Michael, for the talk. I have perhaps a bit too open-ended a question, so maybe if Eleni would ask hers first, then perhaps, but I'll ask mine anyway now, and then we decide if it's too open-ended to be answered right now. I wanted to know if you could share some of your insight as to why exactly you think that linear logic hasn't been adopted by constructive mathematicians at large. This is coming from an outsider, because unlike Juan, I don't describe myself as a constructive mathematician. I'm interested in linear logic for other reasons. So I'd like to know what's the hang-up?
I can probably try to say something about that quickly. So different people have different reasons for wanting to do things constructively. So for me, one of the main reasons that I like to be constructive is because constructive mathematics can be interpreted in categories and in toposes. And toposes arise naturally even in classical mathematics, and I care about those. So for me, the categories in which linear logic can be interpreted don't arise more naturally in the same way that toposes do. And so that was one reason that it wasn't as interesting to me until I noticed something like this, where I can use my linear logic to say something about my intuitionistic logic. For people who are more philosophically oriented towards intuitionistic logic or constructive mathematics, it's harder for me to say for sure, because I'm not really such a person. I think probably part of it is that it's difficult to get a sense for the meaning of the linear connectives if you think in terms of truth rather than in terms of sort of information flow. Linear logic, sort of, you think about it in terms of connecting processes and so on, it makes sense to understand the difference between an additive and a multiplicative connective, but it's harder to understand it to me in terms of truth. What does it mean when I claim that P and Q versus P tensor Q. I don't know what the difference between that is to say that they're true. And so that is also something that I think that an interpretation like this could help with in terms of explaining it a little bit better in terms of truth, or at least provability.
I think that's a good answer. Thank you.
So, Eleni?
Hi, Michael.
Hi.
Great talk. I enjoyed myself a lot. I'm going to ask you something. I mean, it doesn't have to do with linear logic at all, which is strange coming from me because, you know. But anyway, I was really in shock when I saw this assertions and refutations that you had in translation, because this is exactly what happens when you, for example, when you talk about intuitionistic modal logic and you talk about expansions of K with, for example, with what's the name of the property, transitivity, or etc. And what you have when you, for example, when you want to interpret transitivity in the intuitionistic modal logic, you get this thing. You have to get in the axioms. You have to get the assertion and the refutation. So you need both of them at the same time. And it's, when you put the transitivity there, and the ones that you have in the intuitionistic part, they're exactly the same ones that you have when you talk about these things in quick semantics of intuitionistic modal logic. So it's just a comment that I found it really interesting. And I bet, as I said, this has nothing to do with linear logic at all, but I bet that if I take all the extensions that I work in intuitionistic modal logic and compare with this yellow column that you have there, they are going to be exactly the same. So that was really, really interesting. So it's just a comment.
Interesting.
Yeah, I don't know if it has anything to do with what you're doing or not. But
yeah, I'm not very familiar with intuitionistic modal logic. I would be interested to know more.
Yeah.
Thanks.
Well, thanks again.
My turn, Bruno?
Valeria?
Yes. Yeah, lovely talk. That's really nice. But do you mind going back to the BHK interpretation?
This one?
Yep. So you see, I think, you know, this is not just the two construction on a Heyting algebra. That's also the dialectical construction on a Heyting algebra, except that you have to put the implication there too, because intuitionists kind of really want to keep the three different operators apart, right? You want to have implication, conjunction and disjunction, different operators. And, you know, this kind of leads to this question about the fact that the way you're doing stuff is in affine logic instead of linear logic, right? So, you know, if I kind of wanted to keep things more separate, kind of, I mean, first, you know, it would be exactly one of the versions of the dialectical categories that does exactly that, as you know, because you actually did some work on the dialectic. Yeah, and so, you know, I know that you know it. And hence my question is about if one's talking logic, purely logic, you know, forget about our use of, I mean, the use in constructive mathematics is beautiful. I love it. But, you know, if you're thinking just about logic itself, what is the philosophical conclusion that we want to get from that? Is it, I mean, one of the conclusions could be the fact that that for every logical system, you should think about assertions and refutations. That could be one of the possible conclusions. Or it could be that you know, we are kind of forcing things to be symmetric by by inventing I mean, not by inventing, because the negation is very similar to the negation in linear logic itself. But you know, losing this ability to, I mean, the thing that is happening is that in full intuitionistic linear logic, you have this separation of concerns. You will have linear implication, multiplicative and additive conjunction, multiplicative and additive disjunction, and negation. And you know, once you get some formula, you actually know what sort of thing it is. So do you see what I mean? You have this, which maybe it's not what we want. Maybe that's what makes intuitionistic logic difficult when you're not doing it, the linear version of it. But you do have this notion that everything knows where it's coming from. And here we don't, right? Because multiplicative and additive conjunctions are the same. So whenever you get something that starts with one of them, it could have been, it would have been the same as starting with the other, I think.
Multiplicative and additive conjunctions are not the same in this interpretation. Do you mean, are you talking about ordinary intuitionistic logic?
No, I meant in affine logic. I thought you just kind of had a minute ago something saying that you'll use the affine logic thing kind of makes the one equals to the true.
Yeah,
right?
One is equal to true, but tensor and width are still different.
But not for the version that you're using for the mathematics, because I thought
they're still different.
Yeah.
So here's the definition of the additive conjunction, and here's the multiplicative conjunction.
Right. I mean, right. I do know those definitions, right? Because they are the same as.
Right. And so if you're starting from a hiding algebra instead of just a residuated lattice, so that the input tensor and the input meet are the same, then these two have the same proofs, but the same assertions, but different refutations.
Right. That's right. But that is kind of something that is not different from the linear logic itself, because this thing also serves as a version of intuitionistic linear logic, right? Kind of full intuitionistic linear logic.
Sure.
So I don't know. I mean, I made a mistake because I thought you had said somewhere that you were kind of making the tensor the same thing as the width, but clearly not. Yeah. And certainly not on this fake BHK construction, right?
Yeah.
Right, but in any case, you see, it is kind of philosophically interesting to ask: is affine logic more important than linear logic, or more important than intuitionistic logic? What's your take? I mean, it looks very not very pretty to me. You know, the fact that you kind of force the two units to be the same.
Yeah, it's interesting. I mean, I think I generally would avoid making blanket claims about one logic being more important than another one. I think lots of different kinds of logics have lots of different uses.
Indeed.
Ordinary, I mean, Girard's linear logic is kind of like, and he designed it like this, right? It's kind of like a universal system, which sort of you can get all sorts of things out of it by specializing it in different ways. Maybe it's not the most universal you could get, but it's very, very general. You can embed lots of things into it. Affine logic, I've found in the little bit of work that I've done trying to actually prove things in affine logic, it's a lot easier for me to get used intuitively to the idea that I can't use something more than once than the idea that I have to use everything I've assumed, because I'm sort of, I don't want to have to, I'm not used to having to keep track of all my assumptions to make sure that I use all of them. But it's much easier to notice which ones I've already used, so I'm not allowed to use them anymore. I don't know. I mean,
that's a good. That's a kind of a helpful thought that once you use it, you know you've used it, right?
Right.
So if you use it again, you say, "Oh, oops, hang on, that's gone."
Yeah.
But yeah, no, I think I think the point that I want to make is this business that this does not look to me as exactly the two constructions. I think it's the thing that's in the intersection between true and dialectical, and I don't know what do we do with the morphisms. The morphisms don't show up here because
I see what you're saying, because it's so degenerate, because you're starting with a lattice, you can't tell the difference between the true and the dialectica.
That's right. That's exactly.
Yeah. You're right about that. I'm inclined to call it a true construction because I understand true constructions better than dialectica constructions, and like particularly like this adjoint property, right? Like this adjunction generalizes to categories and multi-categories for the true construction. The dialectica construction has different universal properties that I don't understand as well.
Right, but it is actually, I mean, the adjunction there is exactly the one on the dialectica. The true construction, by and large, you have to kind of make a pullback on the second component, right?
Yeah, right. I mean, that's another.
Because it's just, again,
specified.
But in general, you have to put a pullback there. And, you have also this difference between a real product on the second coordinate and a tensor product on the left coordinate, which, again, shows that, something's slightly...
I was going to ask you about that. Is there... like why exactly it's a meet on the second coordinate?
Where, here?
Yes, on the product, on the... it's been nagging on my, like, when you drew attention to it, and I couldn't exactly understand.
Yeah, so there are different ways of explaining that. Here's my favorite way of explaining it.
Could it be that, maybe my guess, you don't have to tell which one of them it is, or no, not? No, go on.
Yeah. So here, my favorite way of explaining it is that you want a proof from a tensor product to be the same as sort of a proof using two hypotheses. That it should have this sort of universal property that the formulas in the context are sort of might as well be combined with the tensor. And then you want to give, you can give a direct definition of this sort of multi-inequality in terms of the inequalities in your original lattice H. So that to prove assuming P and also assuming Q, I want to prove that R. So what should that consist of? Or maybe what should that should be in the, what should that be if and only if? Well, if I have a proof of P and a proof of Q, then I should also have a proof of R. And now what can I say if I have a refutation of P? Well, if I know that Q, if I know that R is, other way around. What can I say if I have a refutation of R? Sorry, I wasn't really prepared for this, right? I don't know I can't refute P or Q immediately because I don't know which of them might fail. All I know is that this implication can't fail. But if I know that if I have a proof of P, then I can conclude that I must be able to refute Q. Does that make sense?
Of course, and then the same with P, and right. Then that's why I said, because you don't know which one is going to fail.
Yeah. Now I can see what you meant by that.
Yeah, because you have those two. You're going to use the fact that you have you're going to use the refutation of R to produce, but you don't know which of those procedures you're using.
Yeah.
Okay, so my intuition was at least in the same sort of same ballpark as the correct answer. Yeah. Okay, thank you.
Any other question, comments?
No, just out of curiosity, what's the program that you use? It's fantastic.
This program is called External. It's External++. It's a Linux program. It lets you open up a PDF and then scroll through.
Yeah. Amazing. I love it.
The slides are just Beamer, of course.
Yeah, sure.
Well, so thank you very much, Mike. It was really funny.
Thank you.
And
Thanks a lot, Mike.
Everybody.
Thanks again for the invitation.
And thank you very much, everybody who was listening. And well, hope to see you again in the next seminar.
Thank you.